To run a traditional farm today, you are entirely tied to a global supply chain. If the diesel stops flowing to the local pump, the tractors stop moving, and the harvest rots in the field. Even if the tractors are running, farmers face an entirely different gamble the moment seeds hit the dirt. It's a germination lottery. Drought, sudden frosts, poor soil conditions, and early pests routinely wipe out huge percentages of a crop before it ever breaks the surface. What if you could step outside of that system entirely? Imagine a setup where a crop's survival has absolutely zero dependence on the weather, and the heavy machinery required to harvest it doesn't need a single drop of imported oil. Right now, modern agriculture is essentially an exercise in managing massive, unpredictable vulnerabilities. We haven't been engineering guarantees, we've just been playing the odds. The biological hardware needed to break this cycle already exists. It's an ancient hardy plant called Camelina sativa. If you look closely at the cross-section of its seed pods, you'll see why it's so valuable. Those dense seeds can be crushed to produce both high-quality raw biodiesel and a protein-rich animal feed. But growing Camelina the traditional way comes with a bottleneck. Sowing these seeds out in a dirt field requires a 90 to 120-day growth cycle. If your goal is immediate energy independence for a homestead, waiting for manufacture guaranteed crop survival inside a highly controlled, closet-sized lab environment. Achieving true agricultural autonomy requires treating biology as a precise, scalable manufacturing process rather than a natural lottery. This process is called micropropagation. Instead of relying on seeds, you take a single cell from a genetically elite, high-performing Camelina plant and clone it inside a completely sterile environment. The sheer volume this method produces is staggering. A basic lab space measuring just 4 square feet can exponentially generate 2,000 perfectly identical plantlets every single month. There is a catch, though. When these clones first emerge from the lab, they are far too soft to survive the real world. Because they've been growing in 100% humidity with a constant diet of sugar, they completely lack a protective waxy leaf cuticle. To fix this, the clones enter a hardening phase called the regenerative nursery cycle. First, you wash all the sugary agar off the roots to prevent rot, and then aggressively inoculate them with mycorrhizal fungi. This biological dip essentially acts as an artificial immune system boost. Next comes the physical stressing. You expose the young clones to UV light and oscillating fans. The wind forces the stems to physically strengthen, and the light triggers the plant to develop that tough, real-world leaf cuticle it needs to survive outside. By the end of this intensive lab process, you have a biologically primed superstarter. You have bypassed the riskiest, most vulnerable phase of the plant's natural life cycle entirely. From there, these hardened clones move directly into a high-density, 10-gallon vertical hydroponic setup. Moving away from soil and feeding the roots an exact liquid diet accelerates the plant's growth by 30 to 50%. This chart maps the primary energy loop. It starts at the hydroponic rack, moves to a fast seed harvest, and goes straight into an oil press. The resulting raw biodiesel provides enough on-site fuel to run a standard utility tractor or a backup generator, and branching off that oil press is a secondary biological loop. The leftover protein-rich seed cake is fed to the homestead chickens. Those chickens then produce the nitrogen-rich manure required to formulate the exact nutrient batch for the next hydroponic cycle. By linking these technologies together, a single operation creates a completely autonomous, zero-waste energy and food loop, operating entirely at the microscale. If a homestead optimizes this lab process, it can quickly produce a massive surplus of clones. At that point, the operation scales outward, shifting from a personal fuel producer into a boutique nursery that supplies robust starter plants to traditional local farms. For the traditional farmer buying these clones, the economic savings cascade immediately. They skip the risky 4-week germination phase, eliminate early season herbicide costs because the plants are already established, and secure near 100% field survival. This uniformity pays off again at harvest. Because every single plant is a genetic clone, the entire field ripens on the exact same day. This allows for a single, precise pass with a mechanical harvester, stripping out massive amounts of wasted fuel and labor. The true product this bio-foundry sells to local farms is mathematical predictability. It provides absolute insurance against climate volatility. This marks a shift from the chemical-heavy expansion of the last century toward a system of biological precision. It moves the critical infrastructure of farming, the production of seeds and fuel, out of global shipping lanes and directly onto the farm site. When thousands of individual farms can manufacture their own fuel and clone their own starters, the food supply is no longer vulnerable to a single point of failure. This creates a decentralized energy and food network that remains operational even if central supply chains or national grids collapse. Modern agricultural resilience is now a factor of technical throughput. By mastering micropropagation at the local level, farmers gain the ability to manufacture their own stability, regardless of volatility in the global market.